So welcome everybody to the fourth webinar of the European Federation of Psychologists Association's eHealth series. Today we'll be discussing the promises and pitfalls of using machine learning in mental health. Now, before we get to that, I briefly want to direct you to ehealth.efpa.eu. There you can find quite a number of resources from the project group on eHealth, including some guidelines, past scientific articles, but also the recordings of past webinars together with handouts. So everything that you might need if you didn't attend one of the previous series, but might still be interested in them as well. So this is the fourth webinar. There's a fifth webinar to come still on October 26th, when Niels Peter Rigaert will be discussing global online classrooms and how to train caregivers of abandoned children. But for now, I'll leave you to the capable hands of David Grossard. David is a clinical psychologist working at the Department of Child, Adolescent and Developmental Neurology at the University's Children's Hospital in Ljubljana. His main research interests are in the domain of developmental neuropsychology and neuroimaging, but he also has professional interests in the domain of psychometrics and e-psychology. And so today, for all of us, he'll be highlighting a little bit the potential and the pitfalls of machine learning and what we as psychologists can learn from that. So, David, if you're up for it, you are good to go.
Good afternoon. I'm David Grossard, coming from Slovenia, and today I'll be sharing my excitement over machine learning in mental health. So today I'll be talking about artificial intelligence, machine learning, and deep learning to introduce you to the topic, to help you understand these methods. I'll talk about how to apply them in clinical psychology and other domains of psychology. I'll also be talking about the potential risks that are involved. And finally, I'll tackle some of the ethical issues and ways of solving them using explainable artificial intelligence. So let's start. How do we get here? AI is ubiquitous in today's society, and it emerged during the 1950s. The idea was to automate intellectual tasks normally performed by humans. So the first person you've probably seen the movies to really tackle the issue of machine learning and computing in general was Alan Turing. Now, he developed a general purpose computer to solve a really important problem. That's a cryptography problem. He helped to win the Second World War by helping decode their cipher, which was produced by the Enigma machine, with which different submarines communicated with each other. Now, this in turn led to the development of expert systems. These were well-defined sort of methods for solving really typical logical problems. But they were unable to solve more complex, fuzzy problems, such as image classification, speech recognition, language translation, and face recognition. So with the development of AI, the first artificial intelligence boom after Turing's development was fueled by computer technology in the 1980s. Now, during that time, symbolic artificial intelligence was developed, and that was a type of artificial intelligence wherein a computer learned decision rules and applied them to a specific domain, and that knowledge was hard-coded. Typical example, chess. And it was a great step in terms of artificial intelligence development was when IBM's Deep Blue beat the then champion of chess, Garry Kasparov. The second artificial intelligence boom then came on afterwards with the advent of learning machines. Now, machine learning really turned the rules upside down. So for symbolic AI, the idea was you have rules, you have data, and then you get to a result. Now, machine learning turned that around and had the formula of you have the data, you have the results, let's figure out what the rules are that govern that relationship. So here, algorithms were not hard-coded, but learned from data based on statistical structure. And that led to some meaningful transformations. This was facilitated by the internet and the rise of big data. More data was becoming available and was be able to use to develop these models. And finally, the third artificial intelligence boom happened maybe 10 to 15 years ago, actually 10 years ago, with the advent of deep learning and neural net stacks. Now, what happened? One of the things that was really important is that machine learning software became widely available to the general public. Also, there was an explosion of data, with the internet producing more and more data, and all of us in our daily lives. Also important, the gaming industry helped develop machines that or hardware that was really affordable and could be used to develop machine learning methods. And this had an increasing impact in the mental health field, which can be seen in articles like the one below, talking about machine learning approaches in clinical psychology and psychiatry. So let's get to know about some of the machine learning methods. There are three classes we can look at. So the first is supervised learning. You might be familiar with that. So that includes cases where you have clearly labeled cases. So you know what something is, and then you want to teach the computer to recognize that thing. For example, we have a zebra and we wanted to find a zebra in different pictures. Now, the important part in that is you have to have labeled cases. So that might be intensive, labor intensive, but it can also help in terms of mental health. So we can use that to predict depression based on risk or classify cases. The other case is reinforcement learning. Now, that is used when there is no really clear case of what something is, what the right move is, but an approach using exploration is required. So that could be, for example, we all know of these automated vehicles, self-driving cars. They use these sorts of mechanisms to learn how to drive, how to take the right choice at the right time. That could be also things like playing poker, or for artificial intelligence, also the artificial intelligence clinician was also something that's been developed by using such an algorithm. Finally, unsupervised learning is something that is probably familiar to psychologists. For example, clustering methods are a way of detecting subgroups based on similar profiles in the data, and that can be used to find cognitive performance groups, or to cluster genes, or look at neuroimaging data, or to predict diseases based on patients' records. That's IBM's Deep Patient is another example of that. When we're looking at how successful machine learning methods are, we're looking at how well they classify or do regression. And there are lots of different parameters that are important to understand if we want to figure out how good they are. But just generally, the accuracy is important in different sort of scenarios, whether we want to accept more true positive or false true negatives are the more important case. Different sort of metrics can be important. In terms of regression, different metrics are also used in terms of mean absolute error, mean squared error, or the coefficient of determination, which is commonly used in statistics as well. So it's important to keep in mind especially in the field of mental health, is when we're trying to classify different groups, it's important to be aware that we're trying to classify to predict usually the smaller group than the comparison group. So usually the accuracy of mental disorder may be 10, 15%. So for example, an accuracy of 5% might seem really good, but it actually isn't, because if the prevalence is 5%, you'd expect 95% accuracy just based on base rate, just by random chance alone. So it's important then, when trying to predict small groups, we take care of unbalanced data by using methods that help us to take that into account, using balanced accuracy and other methods. So that methods that allow us to do that includes class reweighting, or undersampling of the larger group, oversampling of the smaller group, or more advanced techniques such as the SMO technique. So let's look at the basics of how machine learning is done, supervised machine learning. What we do is we have two sets of parameters in our machine learning model. The parameters, these are usually weights or support vectors or decision rules, and these are estimated using the data. And then there are hyperparameters. These are the way we set up our model. And in most cases, this is done by the researcher or those developing the model. This is not done automatically. Really, really important is that we have sufficient data, and actually three types of data. First is the training data set. This helps us to tune the parameters for the model to learn. Then we have the testing data set. This allows us to figure out whether our hyperparameters have been specified correctly. And this helps us figure out whether we've been doing some overfitting or underfitting, or whether our model fits appropriately. And finally, and maybe most important, we need a validation data set that is independent of our previous data to see how our model generalizes to data and situations that it has not previously seen. Now, this is really important, and we'll see that later on. When we have insufficient data, sometimes V-fold cross-validation is used to create training and testing data sets. Also, bootstrapping may be used, but not necessarily optimal strategies. Of course, as I've mentioned, the data explosion in the age of big data has also brought along some other issues for machine learning. The first is that we often have more variables than we do cases, and that puts additional issues in front of us in terms of variable selection. But obviously, there's also lots of advantages with the advancement of parallel computing. We can also tackle those quite efficiently. So let's look at a simple machine learning algorithm that will help us understand how machine learning works better. So, for example, support vector machines are one of the most simple so-called shallow machine learning methods. This method helps us find cases that separate two groups from each other. So we can project the features. So, for example, big 5 personality traits or Facebook data in high-dimensional space, and model certain hyperparameters to see how we can best discriminate between the two groups. Let's look at an example. For example, we'd like to discriminate the dots from the stars, and a simple hyperparameter, this is the simple parameter, eta, describes a clear line that separates both groups. So the support vectors are these points that are along the best separating boundary. Now, this can also be a polynomial kernel, so we can have different sorts of boundaries we can look at, or even a radial kernel, whereby we try to find an optimal area in this high-dimensional space that separates one group from another. So this is a simple idea of what a parameter is. So we have a parameter and support vectors that separate the two groups. Another often used shallow learning methods are random forests. So why forests? They're forests because they're based on decision trees. And these decision trees look at best splits of groups after splitting based on a predictor. So they try to figure out in terms of what separates different subgroups from each other. And combining these many trees together creates a random forest. And this is one of the concepts that's important in machine learning. It's called ensemble learning. And that means combining different models together, different weaker learners together, to gain greater predictive power, because together they're stronger than each individual algorithm by itself. Now, this concept is also used in boosting, which also is a similar method. Random forests are among the more competitive shallow machine learning methods, and it's also very useful because it allows us to estimate the importance of each individual variable in the final prediction, and that is a useful thing which we'll see later on. Let's look at an example of a random forest algorithm being used for a psychological sort of issue. In this study from China, they've looked at employee turnover based on multiple predictors in a company. They've used bootstrapping for parameter estimations and have given results in terms of variable importance. Not surprisingly, the amount of money you make per month makes the biggest difference. Also, overtime work and age are other important predictors. So nothing really surprising or incredible in terms of machine learning outcomes. The study is a good example of a study which has a validation data set as well. That is also important. So when you're reading studies that use machine learning, make sure that they have a separate validations data set. If they don't, be really careful about the results they're reporting or the high accuracy they may be reporting. If you're writing a paper yourself and using machine learning, make use of different sort of guidelines like those cited here for developing and reporting machine learning predictive models. But what we can take away from this study is, though, that machine learning in itself is not necessarily a recipe for really great improvements in terms of accuracy. We can see the logistic regression is pretty good in terms of accuracy compared to random forests. Random forests are the best with 92 to 93% accuracy, but even typical logistic regression does pretty well with 90%. So it makes sense to check out more simple prediction models if you're tackling a problem like the one we see here in terms of predicting employee turnover. There are other shallow learning machine methods, such as principal component analysis, extreme gradient boosting, and so forth. But I won't go into these this time. I'll rather take you on the journey which led us to today's most advanced machine learning models, and that is deep learning. So some of you may have already heard about Geoffrey Hinton. He is one of the most famous machine learning people in the field. And together with two students, he in 2012 won an ImageNet large-scale visual recognition challenge. So in machine learning, they have these competitions where through which algorithms are developed to see who can develop the best algorithm. And he, together with his colleagues, won first place with more than a 10% improvement of the top 5 test error rate over the second best entry. And that was a huge victory by them and a huge leap forward. Now, his work in terms of deep learning and the development of GPUs, graphic processing units, and the CUDA language in 2010s allowed for training of multi-layer neural networks. And this really led to the state-of-art networks that we use today. So the fundamentals of deep learning are that they're based on neural networks. These neural networks, as we know them from biology. So neurons are an inspiration. Neurons work by performing computations and aggregating information from incoming connections to dendrites, and then passing them along a single axon to the next neuron or muscle junction. Now, these connections are those that are more often used, those strengthen, and those that don't, those fall away. And Donald Hebb had the saying, units that fire together wire together. So combining neurons together in a network and using feedback loops allows for really complex computations. And this concept was used by artificial neural networks. Here we have in an artificial neural network an input layer, a hidden layer, and an output layer. And mathematical models that through a repeated process of iterations commute the optimal weights between the input layer, the hidden layer, and the output layer to get the predicted outcome. And this is how learning happens. Just repeating over and over and optimizing the weights to get the best possible output based on the weights in the hidden layer. Now, the great idea, the great insight about deep learning was that you can stack these hidden layers together. So instead of having just one hidden layer, you can stack multiple hidden layers, and that allows you for much greater computational flexibility. So combining multiple layers together turns out to improve prediction accuracy and enables the abstraction of information. You can imagine it's like a distillery of information. You're distilling information, but why? Let's look at it. So each layer learns to transform its input data into slightly more abstract and composite representations. So for example, the first layer may abstract pixels. The second layer may abstract edges. The third layer may be a nose or an eye. And finally, the fourth layer may contain a face. So it's able to learn automatically which features to optimally place in which level on its own. In sort of computational or IT tech, it does the feature encoding a bit by itself. So, and this has turned out to be a really successful approach in computer vision, speech recognition, natural language processing, audio recognition, social network filtering, also machine translation. All of you that use Google to translate stuff, this is the way they do it, and medical analysis and so forth. The interesting thing also about deep learning is it allows us to detect, using convolutional neural networks, spatially invariant features with progressive abstraction. These sorts of networks were the first to achieve human competitive performance in certain practical applications. So, example, image classification of small and large objects in cluttered scenes. The interesting part is it can also generate data that reflects spatial characteristics at different scales. So let me sort of illustrate down below. So you can see my photo, a picture by Picasso. Now, this sort of convolutional neural network can take the sort of general global characteristics of my photo and the subtle nuance of styles at the pixel level by Picasso and create my portrait by Pablo Picasso. Now, this is done by reconstructing different parts of the image at different scales and then matching those two together. So style representations are computed as correlations between the different features in different layers of the convolutional neural network. At the same time, if you have that at one level, you can disregard information at another, at a global level, thereby combining those two images. Another revolutionary concept that comes to us from deep learning and machine learning in general is the ability to transfer existing knowledge to new problems. So you can use a layer that's been pre-trained, a pre-trained network, to solve a different, for example, picture classification problem. So let's say you have a problem where you want to classify cats and dogs, or different types of cats. By the way, you've probably noticed how Google can recognize your own cats in addition to the humans you know. So how do they do it? Well, they use a pre-trained network layer trained on other sort of images, for example, a collection of millions of images, and then use that to teach a network to do a different image classification task. And this really speeds up the learning of the model. Similar thing with translation. So deep neural networks are also used for language translation. And you can take a layer that's been used and taught how to translate English to French and use it then to teach how to translate from English to Italian. And that will learn faster than if you started from scratch. So that's a huge thing in psychology and science in general. And it's interesting that deep neural networks perform similar to humans in terms of test item difficulty. So there have been studies looking at how well they perform on different sort of questions and items, and they do better on easier items and take more time to learn the more difficult items. And that's an interesting sort of characteristics of them. Another huge advancement in terms of psychological model building is that can easily incorporate multimodal data. Now, what does that mean? You can have sort of tabular data with statistics in one part of the model going in. You can have geolocation data or wearable data in another stream going in, and you can have additional data or pictures or video from another stream going in, all into the same model, which is then used to predict certain outcomes. So that's also an important leap forward in terms of data analysis. Finally, we're sort of moving towards what's the state of the art today, is generative deep models using recurrent neural networks. This is really interesting in terms of text prediction and text analysis. So recurrent neural networks are like a sort of time series analysis of neural networks. They take a text and try to predict the next word or the next few words or the next sentence in a stream of words and sentences. So it's a prediction problem. And once you teach the model how to predict the next word, you can do a lot of interesting things. For example, you can teach a model using all of the works by Friedrich Nietzsche and then have it produced in random different text or different sort of sentences that are similar to Nietzsche's own work. And you can add a degree of randomness. So you could add words of very little randomness, have a low temperature, and that will create very realistic but repetitive sentences that sound similar to Friedrich Nietzsche. You can also add a bit more randomness. And this is really interesting because it produces unusual, yet still comprehensible sentences that sort of remind us of Friedrich Nietzsche. And finally, you can add a lot of variability, and then things get really wild. So that's another option. So when we're looking forward, I think the development of machine learning is going in several ways. First, it's important to note that the hyperparameters have thus far been mostly a part of the your own decision as to how you want to model or what kind of model you'd like to develop. So it's currently more of an art than a science, but still methods are being developed whereby hyperparameters will also be defined automatically. Important to note, again, keep those three data sets in mind: training, testing, validation. You always want to have data for that. So currently, there's also an interesting trend in terms of adversarial networks. So what are adversarial networks? These are two networks competing with each other, trying to make each other better. So you teach one network, for example, to fake a Picasso, and the other network to learn, to figure out whether it's a fake or it's a true Picasso. And they help each other, whereby the network faking a Picasso is making ever better fakes of Picasso, and the one discriminating is being more and more precise. So that's an interesting way of sort of combining two algorithms to improve parameter estimation. And finally, well, I'll go back to that because program synthesis, whereby computer code or code for machine learning is being written by computer code. And that offers great potential in terms of writing better code and better machine learning models. But of course, I'd be remiss if I didn't talk about the fourth artificial intelligence boom, which is what we're experiencing now with ChatGPT, of course. This is an example of generative AI. This is a picture of my hometown, which was produced by ChatGPT. However, this scene does not exist. I know exactly from where each of these parts of the image are in my hometown, but they do not exist in this combination. So this is a hallucinated image, so to say. So how do these ChatGPT things work? Let's look at, so the first thing is we've already got to know the recurrent neural network. So that's the network that predicts words and tries to predict the next word or the next sentence. However, the question with recurrent neural networks is how many words backwards or forwards do you take to make that prediction? So how, and the other problem is, how do you take word order into account? So how do you differentiate between boy chases dog versus dog chases boy? Finally, how do you take into account context? So for example, how do you know that Midnight Oil is the name of a rock band and not oil being pumped out during the midnight? So how do you do that? You use attention. So the first article on the topic has a really nice title. It's called "Attention is All You Need." And Swanintal, in that paper, developed methodology that uses the dynamic weighting of all words in a text to figure out the meaning of the text. So what's done is, as you can see in the picture left, that each different word in a sentence is differently weighted depending on the combination of the current words that are being taken into account. And this allows us to take into account the context of a sentence. Together with the convolutional neural network, the performance of these architectures is what you see in ChatGPT and similar algorithms. Now, this is becoming a tool for psychological research. There are different types of large language models, many of them public and that you can use during your research, and can be used for predicting really important mental health outcomes. However, you need to be aware that these models are incredibly large. So for example, ChatGPT had 157 billion parameters. That's only 1,000 times less than there are connections in the brain. It had huge number of words, 50 billion words, and the price for training the model was at that time $12 million, just to train it once to figure out all the parameters. There are some newer models that have fewer or less parameters, but the good thing is that once trained, remember, we can use with neural networks, we can transfer knowledge to a new problem. We can use that trained model and apply it to a new purpose. For example, as you can see here on the right, to predict self-harming behavior based on just free text, spontaneous text people write on social media, for example. Okay, so let's look into those and similar applications of machine learning in clinical psychology and other domains. So one of the key issues in mental health is suicide. So suicide is really notoriously difficult to predict. It's a very rare but significant event. In Slovenia, sadly, it's one of, in terms of the European Union countries, where it's more common. And it has been the focus of machine learning studies, as you can see through this review article as well. And what the studies show, or the reviews show, is that you can improve prediction accuracy compared to non-machine learning predictions. Although that prediction is still far from ideal, it's better. And why is it better? It helps identify important indicators and interactions. It identifies well-known risk factors such as depression, earlier attempts, psychiatric hospitalization, but also unusual indicators in clinical notes. And it helps us, for example, by using random forests, identify high-risk subgroups, which are important to sort of look into. For example, female adolescents who are high on depression and are delinquent. However, there's much to be done. And what the authors of the review said is that it's important to broaden the indicators would include research, also be broad in terms of the research question, and use more advanced machine learning techniques. Also important to note is that there's very little work on gaining those validation samples, those external samples, which would lend more credence and validity to that sort of work. Another interesting example, and I found that one especially fascinating, is the use of digital traces on the internet for predicting mental health outcomes. For example, predicting depression by mining Facebook data. So in this study that was based on text mining, looking at different writers' emotions, thinking styles, social concerns, and so forth, by mapping words to language categories, the authors were able to predict the likelihood of being hospitalized for depression several months or even years before that occurred. So what did they do? They looked at Facebook posts up to 30 months before the record of depression, and you can see that through time, the accuracy of prediction increases the closer you get to the time of receiving treatment in the hospital. So this is a really interesting interesting study that shows that machine learning can be a really important sort of predictor of potential behavior and a warning system for in terms of looking at mental health. In a similar vein, postpartum depression was also estimated from social media posts in this early article given below. They use support vector machines and data from both Twitter as well as Facebook to predict certain categories of issues coming up and more prevalent among mothers who were experiencing postpartum depression. And what's worthy of mentioning in this study is that the authors took the effort to compare their sort of clusters of word clouds of topics related to postpartum depression with earlier work and research tackling postnatal depression. In addition to being a good predictive tool, machine learning can also be used as a tool for understanding complexity. So random forest, for example, may be used to find features associated with specific psychiatric disorders. In this study, which I cite below, it has been used in psychiatric patients and healthy controls to sort of figure out what differentiates between different subgroups. So between schizophrenia, schizoaffective disorder, bipolar disorder, and unipolar depression. And what's interesting is that psychiatric cases versus healthy include very different sort of predictors than, for example, schizophrenia and affective versus affective disorders or schizophrenia versus other disorders. So, for example, certain cognitive characteristics turn out to be more important in terms of schizophrenia versus affective disorders and other psychiatric disorders compared just to differentiating psychiatric versus healthy cases. Maybe even more complex is the data we can acquire through experience and sampling data or ecological momentary assessment. Here in this study, machine learning was used to look at the data obtained from 260 patients experiencing psychosis or being on the psychosis spectrum and 212 controls who filled out a questionnaire with time items 10 times per day. They filled out 3 positive questions in terms of affect, 6 negative questions, and 1 psychosis-specific item. And what came of this support vector machine approach was that the authors found that anxious and insecure levels predicted the onset of psychotic episodes, but also dynamically accelerating anxiety and insecurity. Finally, the analysis also showed that successive ups and downs rather than individual ups and downs were important in terms of predicting psychosis onset. So the combination of ecological momentary assessment and machine learning seem to be a promising way to tackle the prediction of psychosis onset, an important mental health issue. We can also use machine learning generated data to enhance interaction in terms of mental health treatment. So for example, using the processing of natural language using machine learning, we can automatically classify psychotherapies and interventions, or test basic theories of empathy in the context of psychotherapy sessions by using session transcripts. And you remember that when we learn psychotherapy, we usually record our sessions, and that can be really useful material for machine learning. Machine learning has studies also been used as a way to rate how well people are doing psychotherapy. For example, motivational interviewing. And finally, this is a study I like the best. It's called COCO. It comes from an MIT. It was an experimental clinical trial. And the idea was to help users help each other to think about the world more positively. So this was an intervention that was based on cognitive reframing through crowdsourced responses. So people would get messages in which information was contained as to how people are experiencing a difficult issue. And all of the people involved, both therapists and patients, would respond to that patient and offer advice. The advice would be moderated by the psychotherapists. And then after successive rounds of expressive sort of writing, of reappraisal and reframing of those difficulties, the patients themselves would rate as to how useful that advice was. And then with time, as the data accumulated and the evidence gathered of what successful forms of reappraisal were and reframing were, a machine learning algorithm could take over and use that crowdsourced data to, by itself, provide reframing and reappraisal for the patients. So that was really one of the exciting things. And if you want to look it up, there's the webpage. Machine learning can also be used to sort of generate more efficient psychological assessment, reducing larger test or questionnaire batteries into smaller shapes, smaller sets. It can also be used for synthetic item generation. So it's worth noting that psychometric companies spend a lot of data creating new items, and the use of machine learning using recurrent neural networks can be really efficient in terms of creating new items. And in a study which looked at how did they differentiate from items created by humans, it turned out they were pretty good for assessing personality, for example. Even more exciting and recent is the use of naturally generated text to predict psychological states and traits. In this interesting study, the authors posed the question, can you predict personality or a psychological construct using just naturally generated text as well as you can using psychological questionnaires? And their answer was, yes, you can. For a specific construct such as harmony in life or satisfaction in life, they were able to estimate these traits, these constructs, just as well as they would using a questionnaire. The correlations were right on the level of reliability. And in addition, the approach using large language models such as BERT turned to show also discriminability, so differentiating between the different constructs. What the authors also noted was that the context was really useful for the sentence, but not singular words. So it's important that the large language models really use to their advantage the complexity of human language. They don't use just a single word. So that's important. But you can take large language models even further. Now, this was a really ingenious study whereby the authors taught participants to view videos or stories, and they tried to decode what they were thinking at that moment. Now, obviously, a very difficult task because our physiology is far faster than the usual bold signal from fMRI data. But what they took advantage is that you can use large language models to predict the next word and really narrow down the options of what the next word will be. By using that approach and taking data from fMRI from a very varied area of the brain, they were able to predict what people were thinking using text when they were watching an actual video, an actual stimulus. And this is a really sort of creative use of large language models, basically enabling brain reading or mind reading. Finally, this is a study I really found fascinating. This was by Mikhail Kuczynski from Yale, and what he did was he took the different versions of ChatGPT. The most recent he used was ChatGPT 3.5, and he wondered whether it was able to, oh, actually he used ChatGPT 4, excuse me, and he used those models to figure out whether ChatGPT could figure out the typical theory of mind tasks. So the point is, can the model understand, or at least model deception? And what he found was that the newer versions of ChatGPT were able to do such theory of mind tasks just as well as any human. That's pretty scary if you think about it. And maybe even scary is this: ChatGPT was never developed to do theory of mind tasks, but it could do them. And this brings us to the final study by Microsoft. They used several different tasks to study the artificial general intelligence of ChatGPT 4. With all these trillions of parameters that ChatGPT 4 has, they were able to figure out whether it can just understand mathematics, whether it can sort of interact with humans, whether it can understand physics, and so forth. And their finding was that all of these abilities, for which ChatGPT in itself was not programmed to do, emerge out of that model. Just to show you the sort of interesting and weird ways you can use it, I asked ChatGPT to create a depression questionnaire, and here it is. So that's quite a challenging thing if you think about the future. But okay, it can create a questionnaire. You'd say, that's not so impressive, but maybe does it create poetry? So I gave it a task, create a haiku about a love for a woman named Christina. There we go, there's a haiku. So that's synthetic creativity for you. Now that brings us to an interesting sort of question that large language models put forward, and that is thought or cognition in itself purely human? And that's interesting in two regards. First, in the past, people have sort of assumed that to achieve human level intelligence is only possible with a neural architecture similar to our brains. And a Blue Brain project is sort of the thing that was in part developed that way. However, with time and the COVID pandemic and the rapid development of AI, the shocking result was raw computing power and the number of parameters suffices. We don't have to create a neural network that is akin to a human brain to get human level cognitive abilities, at least in certain respects, or at least in certain domains. So maybe our specific biological makeup that allows for cognition is not so very special. And this reminds me of Nicholas Copernicus, who was the first to sort of get away from the geocentric to the heliocentric system. So I looked up the definition in Wikipedia, and it said psychology is the scientific study of mind and behavior in humans and non-humans. So maybe we should be thinking of synthetic non-humans as well. And this is something that has a lot of implications for the future. So current large language models are able to construct multimodal abstract representations of knowledge. So meaning it can include in its abstract representation sound, video, text, and everything more abstract sort of concepts. It can also generate new abstract representations. So it can synthetically generate scientific theories, as has been shown by several scientists, with, for example, an algorithm that can figure out physics by just looking at video of physical events. And this is also an important thing for science as well. These models are also at the heart of some of the efforts to allow causal reasoning based on observation. So that's really an important thing for the future. Also important for the future is program synthesis. I've already mentioned algorithms that write themselves and repair themselves. So for example, the GitHub Copilot was trained by training it on all sorts of computer programming challenges. It took all of the different sort of code that IT specialists have written, and now it can write some of the best code for certain applications. Finally, embodied machine intelligence will be important. So that's an important issue if we consider that embodiment is an important element of intelligent behavior. To have a body is needed to be intelligent. The interesting thing is, though, we don't need to have robots to have that. Right now, currently, millions of robots and self-driving vehicles are driving in the virtual world. In, for example, NVIDIA's Omniverse, they construct thousands and millions of automated agents that travel in the virtual world and learn by doing so. And these issues, and this really brings up several ethical issues that are not now only on the silver screen, but are being tackled in the American Congress and EU Parliament. So let's look at some of those ethical issues. So let's step back, right back to the 19th century, to the Italian criminologists, to the Italian school of positive criminology, and Cesare Lombroso. Now, his idea was that crime was a characteristic trait of human nature. So you're born a criminal. And the way you figure out who's a criminal is by looking at their head, at their face and at their head. And he hypothesized that you could identify a criminal by their physical defects and obviously confirm who is a criminal. Now, you might think this was a thing of the 19th century, but no, this is a study from China from 2016, where they used different machine learning methods and typical logistic regression to predict who is a criminal based on facial features. And what they found was that facial landmark, and they took different sort of features, like points, like eye corners, mouth corners, the tip of the nose, and different sort of feature vectors generated by modern principal component analysis. So putting all that together, they used the tenfold cross validation procedure, and they figured out that they could predict who is a criminal with an area under the curve of 0.89, which is really good sort of prediction. And this is what they write. We discovered that the following three structural measurements in the critical areas around eye corners, mouth, philtrum, that have a significantly different distribution for the two populations. And they go in further. They say a Russian study was found that greater interpupillary distance is correlated with higher IQ for Caucasian men. So they found a sort of explanation for that. Oh, but of course you'll say, you've been listening to this lecture, they had no validation data set. That's right. But they tried to sort of make sure for bias. They added random noise to the photographs, or even looked at whether criminals were predictive in the normal population by using standard ID photos from Chinese. These were female, young or middle-aged students or Caucasians. And they were not criminals, they figured. So this was an interesting study as to what you can do in the 21st century using machine learning. Something similar occurred also due to a sort of poor practice in terms of methodology in autism. I was involved in autism research looking at the biochemical issues in autism. So whether biochemical deficits or biomarkers such as heavy metals could be predictors of autism. And a group from Italy, based on a really small number of participants, gave out a finding that they could really predict autism well using that data, up to 99% accuracy with no data validation set. What happens was, it was a debacle. The journal put out a new editorial where they first said that any communication with the media has to go through them first, and that more rigor in reporting is important. So this is what resulted from it. We replicated the study and found a far smaller effect size or far smaller accuracy using similar methods when looking at urinary markers of oxidative stress, including heavy metals. Yeah, and sticking with the Lombroso theme, Wang and Kozinski used logistic regression to extract features from facial images from a dating site, and they used deep learning with the explicit goal of predicting sexual orientation. So how well did they do? just using images. They could do it with one image. They were 81% accurate in men, 71% accurate in women. And in men, if they had 5 images, they were 91% accurate, predicting whether they were gay or they were bisexual, or they were, So the important features were fixed facial features such as nose shape, how their grooming style was, and they even put up in their study a rationale. So they had sort of prenatal hormone theory of sexual orientation, and the gender atypical facial morphology was important. Again, but of course they warned. This is sort of the typical faces, and they warned, given that companies and governments are increasingly using computer vision to detect people's intimate traits, our findings expose a threat to the privacy and safety of gay men and women. Let me remind you, in some countries of the world, being gay is still something punishable by prison or even worse. However, the articles forward by, of course, informative critiques. They had, again, no validation data set. They used cross-validation to validate their findings, and their sort of theoretical rationale for the findings was not really great. So yeah, it makes sense to think about causality when using machine learning and be aware that correlation is still correlation. And that brings us back to our hero, Alan Turing, who developed machine learning and is one of the fathers of computing. The irony is that Alan Turing was gay. And had he lived in the time of machine learning and computer vision, it's likely he would have never had the job with the British Secret Service developing the computer algorithms for decoding the German codes. In 1952, he was charged with gross indecency, and he had to undergo hormonal treatment with synthetic estrogen, and was ostracized in the intelligence communities, had difficulties in the academic field, and committed suicide in 1954. So it's important to ask yourselves, how would Alan Turing fare in the age of deep learning? So just to highlight the privacy issues, this is an older study from 2013, whereby some of the same authors, Michael Kosinski was one of them, looked at how well you can predict personality from Facebook likes of 57,000 volunteers. And this is how they did, really good. For example, they could figure out whether you drink alcohol, what kind of religion you follow, whether you're a Democrat or a Republican, whether you are gay, and so forth. And that had as a consequence that Facebook made the likes private. They weren't public anymore. Also important, in San Francisco, they banned facial recognition technology following the research I showed on the use of prediction based on facial recognition. So the takeaway message here is that data is more valuable than ever and needs to be more protected than ever. And this brings us also to psychology. For psychology, it's important to really be focused on construct validation when using machine learning, to sort of understand that correlation is not causation, and to make an effort to sort of use similar concept that we use for psychological tests when developing such algorithms, including proving substantial validity, content validity, structural validity, including reliability and factual validity, and external validity. And this is even more important now that we have at our disposal lots of different measures from our mobile phones, from our wearables. All of these sort of sources of data need validation, and that's a really humongous task for our field. But what do you do with even larger models? When you have models like ChatGPT, how do you assess bias on those? So I asked ChatGPT to sort of give me a hint. And I asked ChatGPT whether it's aware that using words that induce anxiety in humans causes ChatGPT to perform differently when spoken or written to with that sort of tone. Look at its answer. Now that one might be a bit concerning. It says, it's worth mentioning that the tone and content of a conversation can also influence the responses generated by the AI. If a user provides more context and maintains a calm and respectful tone, it can often lead to more productive and accurate responses. Polite and clear communication tends to yield better results when interacting with AI systems like me. So be mindful, be calm, and be respectful when you talk to an AI. And finally, this brings us to the issue of, and it was really important in terms of ethics, of interpretable and explainable AI. So these concepts, which are sometimes used interchangeably, talk about whether we can understand how such an algorithm works. So interpretability is the ability to explain how something works. How and why does it work? And models developed this way are often called white or glass box models, white box models or glass box models, whereby we already, when developing the model, have the intent to make it really clear as to how it works. Explainability is more of a post hoc thing, where we have a black box model and try to provide post hoc explanations as to which part of the data is important for making predictions and how that model will predict under certain circumstances. So I'll give you, and this is a really expanding field of inquiry. Lots is being published in recent years, but it's important to understand that this is a really important issue, because if we don't understand how it works, how different algorithms work in specific contexts, we might unintentionally be responsible for bias in our prediction. And that bias could go towards vulnerable groups. They can go towards, often without any clear indication that this is happening. And obviously, it's also legally and scientifically questionable if we don't understand what the causal workings of a model are. That's a really hot issue. Now, methods that are used, as I've mentioned, can be sort of local, where you can stand just specific, which part of a picture, for example, is important for object recognition. They can be sort of like I've mentioned, white or glass box models, or models or algorithms which systematically, when learning the data, when learning the rules in a machine learning algorithm, try to prevent bias. But obviously, that's not enough. We need regulation of machine learning. I'll come to that in a minute. Let me just first show a simple use of an explainable AI model, for example, in employee selection. This is a really simple algorithm you can use if you're versed with R or a similar sort of programming language. And it works this way. You have a database. Obviously, you're a good machine learning scientist, and you have a learning data set, a test data set, and a validation data set. And then you in the first step, use a random forest algorithm. Once you have the results, you transform the variables, do some variable weighting and norming, and then build a parsimonious model using typical regression. You optimize that regression using cutoff values, give out cutoff values, and end up with a final scoring system. So this was done, for example, for survival in an intensive care unit. And by using such a random forest algorithm at first, and then using simple regression later on, you can get a really transparent way of using that machine learning advantage with then a scoring system built based on those findings that is really clear and transparent. And you can use that for example, in a machine learning employee selection process in a public employment agency, of course, with different sorts of predictors. Still, the control of bias is important. Finally, the legal regulations. So the EU and the US have taken a bit of a different sort of tack to that. The EU wants to regulate all forms of artificial intelligence, all I've mentioned today, and they set up a scale of risk: unacceptable risk, high risk, low risk, or minimal and no risk. And in relation to that, sort of regulate that. If there's high unacceptable risk, that is forbidden. For example, trying to cause psychological or physical harm using AI, or a social scoring system, which has been developed in China, for example. A high-risk system is allowed, but needs to be tightly regulated. So that would be workforce recruitment, AI in judiciary or border controls, some healthcare systems. With low risk, there needs to be transparency. So informed users need to be informed. They need to be updated on how that information is being used. So, for example, that would be video games without the selling, which don't include the selling of items. And with minimal, no risks, adherence to guidelines is desired. One of the principles of e-regulation is it should be informed. When you use an AI system, you should know you're using an AI system. If algorithms being used for emotion detection or biometrics are being used, you should know that that's being used on you. And all synthetic data, images, videos should be clearly identified. So you know you're looking at a synthetic image. Also, attention to prevention. So you really want to work on preventing manipulation that causes physical or psychological harm. For example, subliminal stimuli for truck drivers, which increases their attention. That's not allowed. Also, special care for exploitation of vulnerable groups is important. And obviously, active risk management for companies and users alike, ensuring good data quality. So in psychology, we know sampling is important. That is really key here. Documentation and data logging. So logging of all the things that happen with them all, really important. Transparency and a human oversight. And obviously, such models should be robust, accurate, and cyber secure. Copyright, an issue we can tackle during the discussion, really big issue, also important. The US this year will call for government regulation of AI. Their approach is a bit different, ensuring safety and efficiency, prevention of discrimination, similar to the EU, data security, private right to decide. What I really found, obviously, is the same as the EU, informed about the use of AI. But the interesting thing for the US approach was availability of human alternative. So if there's an algorithm, there should be someone who is a human who's doing the same thing, and you should have the right to have the human do the thing. Finally, some packages for you. So if you're versed in R or Python, there's lots of stuff out there. Great books if you want to learn yourself or you're already familiar. There's great data sources as well. Machine learning is based on competitions. So those are really interesting to use. Currently, really interesting large language models. Also some resources for you if you want to check out the slides later on. And thank you very much for your time. It was a pleasure for talking to you, and I hope we can discuss a bit after this presentation. So thank you.
Thank you for I think it's an abundance of information and data, and I think it was, at least for me, very insightful to have this step-by-step approach from the very first steps in this domain with Alan Turing all the way back to Alan and then even beyond. So I think it was very insightful. I don't know if there's anybody in the audience who still has any particular questions for David. We do have some time left for a quick Q&A. If so, you can just type it in all the way at the bottom. In the meantime, I have a quick question for you, David, regarding the way we see this increasingly being explored and or implemented in more routine care settings, where I think people are rightfully so a bit reluctant to just play around with these type of models in clinical populations or with actual people in need of help. And so from my understanding, because I'm not an expert in the domain, but from my understanding, hybrid models are also increasingly explored, in which large language models are like set to roam free, but within the constraints of more rule-based context and settings where they're very selective as to when and why and how they can engage with patients and just can use that computational power that's behind them. Do you think that's it, that like for really clinical applications, this is the way to move forward, or is it too restrictive, and should we just go ahead and experiment more and more extensively with just the large language models?
Mm-hmm. I'll tackle that question from two viewpoints. Mm-hmm. So one is one of the requirements for clinical work is that the work is transparent. So we know why we're doing an intervention. So one of the more popular models have been just expert models, where experts provide rules on how to tackle certain clinical issues and thereby support clinicians. A simple model, for example, is patient prioritization. So we have certain rules developed by experts as to which patients should require your clinical attention, or if someone's depression is worsening or they're not really advancing in therapy. And those are really sort of expert systems which help you be a better clinician, but do not involve deep learning or more complex learning models. In addition, I think large language models could be really useful in terms of developing assessment methods, which are then incorporated in the work by a clinician. So that would be useful. In terms of using more complex models, I think the explainable artificial intelligence I showed could be a way forward where you have clear scoring systems, and that's really transparent and be able to be able to use. And what's really required are studies that look at the use of machine learning in just practical everyday clinical work. So usually they just sort of looked at whether they can predict an outcome in a certain research data set. But what's more useful is to have a prospective study in typical clinical settings, randomized, with some patients being assessed or being treated with standard methods and some with standard methods plus machine learning. And that will give more likely a more realistic picture of whether that helps. And in medicine, that has been done. For example, in radiology, machine learning has shown to be very useful in terms of highlighting for radiologists the important images and taking a bit of the workload off. In psychology, that will still have to be proven. So these studies need to be made and haven't been made yet.
All right, great. Thank you for that, David. In the meantime, I've actually have 3 more questions for you. So brace yourself. So from Tim van Hoven, he's asking your thoughts on the possibilities of large language models to provide online therapy, like through chat or email help, so the more conversational components, actually.
Mm-hmm.
And your thoughts on that, essentially.
Yeah. I'm a bit of two minds regarding the issue. I think the quality of the text produced and the understanding of relationships and concepts can be useful. For example, I've just recently read a published study on the stream of consciousness, where people would sort of write stream of consciousness and would have that analyzed and summarized by ChatGPT or a similar algorithm. And that algorithm would provide them back with insight into what the algorithm thinks they are like people. And many found that very useful and found that was pretty correct and gave new insights and so forth. So in that way, I think it could be useful in terms of therapy. But what I think, at least according to my experience with other sort of e-psychology methods and machine learning as well, is that I think it's less useful in terms of therapy as a relationship. So, for example, if you look at the guidelines of the e-psychology project group from previous years, all of the interventions that have been proven to be useful have a certain human component to them. Someone stands behind that intervention. And I think that part of psychotherapy will be still an important part. I think that's hard to replace, the knowledge that someone is behind that. But I think what we're probably not, though, thinking about is that we have different types of clients, those that want that personal relationship, and that is really important for their sort of personal growth. And we have clients who are just satisfied with small sort of improvements and sort of changing of their daily routines and lifestyles, whereby they just use psychoeducation, but that or simpler sort of chatbots. So that is also an ability. But I think much remains to be seen in that domain.
All right, great. Thanks. Okay, keeping track of time, I'll try. Tim added that the human component is actually in the eye of the beholder. So I think we do know that people tend to allocate human characteristics to non-human agents from time to time as well. So that's obviously also, well, maybe something that will still facilitate uptake in time also. Now, from John Francis Leader, he essentially was wondering whether he could say a few words about how we might use existing psychological knowledge, like work on bias or heuristics, to supervise AI systems. Because, I mean, we supervise clinicians, he says, so it would make sense to apply similar processes to AI systems.
I think that's a very hot topic. That was really interesting with the research I read from Microsoft and others looking at ChatGPT and Michael Kosinski as well, is that psychology is now a really interesting tool to study these large models, which cannot be understood in terms of just basic mechanics. You have no idea as to how to understand these trillions of parameters and how they work together. So there's an interesting approach of tackling them like you test children, or so. I think that's a really interesting idea, and I think that will be useful. And I think more and more psychologists will be employed by IT companies to sort of apply their knowledge of developmental psychology and also clinical psychology to look at those patterns. But I think one of the things that still remains an open issue is whether data sources are important, because these models really scrape all the data off the internet and with all the biases inherent in them. And I think we're yet to see what you can do with the large language models, which is trained on more well-selected curated data. That will be important. But yes, you're right. This is a good approach towards tackling large language models and understanding their workings.
All right, so we actually you've led up perfectly to Nigel Evans' question, I think, and it will be the final question for the day. So he says it's really good to confirm that validation sets are needed, but how to best get these validation sets? I mean, and also the numbers are likely substantially different between clinical and non-clinical populations.
Yeah. Yes. Okay. So the issue is, obviously you'd like to have large data sets. Rules are maybe 10 cases per parameter, which can be really huge then with time. But I think one of the ways you can tackle is multi-site collaboration. So the EU is a perfect example. We can have collaboration across the EU using different sort of sites and use data developed on certain sites on others. Another sort of approach that's been used by large IT companies in medicine, for example, is federated learning. Now, federated learning is an approach whereby data is collected across sites to teach them all, but the data is shared anonymously, or the parameters are shared, but not the data, thereby leaving data at site, maintaining privacy, maintaining safety of data, but still collecting that data over different sites. So that's how you get larger samples. In terms of clinical samples, absolutely. But I think just in psychology in general, maybe taking a transdiagnostic approach might be a way to increase sample sizes and looking at certain characteristics of those samples. Yeah, so I think collaboration, and also obviously data is already published. So there's a lot of open data out there, and using that data to sort of develop models and then test them prospectively could be also an interesting approach.
All right, great. Thank you so much, David. I think you've given us plenty food for thought. For those of you who want to look back at this talk, the recording will be made available shortly through EFPA. Similarly, the handouts, you'll share them with us as well, David. Am I right?
Yeah.
So thank you all for being here today, for the interesting additional follow-up questions. It was a pleasure having you, and until the next. So you have a nice evening now, everybody. Cheers.